Hello Internet, welcome to another tutorial in the series of analog communication systems. In this tutorial we'll talk about Superheterodyne Receiver. In the previous tutorial we did TRF receiver, which is tuned radio frequency receiver. Superheterodyne receiver is an improvement over TRF receiver. I highly recommend that you watch my previous video because some of the blocks in Superheterodyne receivers are similar to the blocks of TRF receiver. I would not explain those blocks in detail in this video. However, I'll explain the newer blocks which are implemented in Superheterodyne receivers in more detail. So that being said, let's talk about Superheterodyne receiver. First things first, we need to understand what heterodyning means. Now, if we talk about the word heterodyne, it means that mixing two frequencies together to make a new frequency is known as the process of heterodyning. So, if we were to define this, we can say mixing two frequencies to generate a new frequency. So if you understand the rationale and meanings behind the terms of this receiver, it will be more easier to understand the whole concept. Now over here I like to highlight these two blocks, and these two blocks are mixer or detector blocks, and they are being fed with two frequencies. As you can see, this mixer stage or mixer is being fed with two frequencies here, and this mixer is also being fed with two frequencies. So I'll talk about the first stage of mixing, which happens right after the RF amplifier. By the way, if you've seen the previous video, we know that antenna is responsible for receiving the electromagnetic signal, and it is responsible for receiving FC, which is the carrier frequency of desired station. So FC is received by the antenna, which is further amplified and in amplitude only. So what we get at the output of the RF amplifier is the carrier frequency. Now over here we have a local oscillator which will produce a fixed frequency of FL. So now you see that the mixer or the detector here in the first stage is being fed with two frequencies, FC and FL, and this mixer can either do a job of generating a new frequency by adding or subtracting FC with FL. So we've got two options here, that we might get a new frequency by either adding the two frequencies or by subtracting two frequencies. So that is where we'll get answers to our two questions. The first question is, why is this mixer known as a heterodyne mixer, receiver mixer? Because the two frequencies that we have chosen here, FC, will not be equivalent to FL. If these two frequencies are different, the output will be a new frequency, and this mixer is known as a heterodyne mixer. And if these two frequencies are equal, this is known as a synchronous mixer. And this condition will lead us to a heterodyne mixer. And please understand, this condition is being used at second stage. So second stage mixer is a synchronous mixer, and the first stage mixer is a heterodyne mixer. And this is one of the most critical points to remember in heterodyne receiver. A heterodyne receiver is a heterodyne receiver because of the presence of first stage mixer, which is a heterodyne mixer. Rest all the stages are synchronous mixing stages, because in this simplified receiver block diagram I have drawn only second stage of mixing as synchronous mixer. However, you can have n stages of mixing after the IF amplifier stage, and no matter how many stages of mixing you do after IF amplifier, they are all going to be synchronous mixer. And the second question is why FL is kept greater than FC and the resultant output at the first stage, which is F5, or which is known as the intermediate frequency, is obtained as FL minus FC. The reason why FL is chosen to be greater than FC is that the antenna and the RF amplifier are connected using a ganged capacitor setup, and if we keep the value of FL smaller, it results in a mismatch of capacitances at the ganged capacitor arrangement at the antenna and the RF amplifier. So this is what you need to commit to your memory. And the reason why we subtract FC from FL and not add it is because the carrier frequency is pretty high and the baseband signal is relatively low. So we want to approach towards a lower frequency, and getting a lower frequency at the output of the mixer can only be obtained if we subtract FC from FL. So had we added FC into FL, we would have even gotten to a higher range than the carrier frequency. We want to eliminate the carrier frequency from the detection stage. So subtracting FC from FL will facilitate that, will help us in lowering down the frequency, and that's the reason we subtract FC from FL. And a very popular value of intermediate frequency is 455 kilohertz. So most of the times we keep the value of FL to be greater than 455 kilohertz than FC, so that the difference between the two at the output of the first mixer comes out to be 455 kilohertz. And the next question that arises is that why is this value kept fixed at 455 kilohertz and not at some other value like 500 kilohertz or 1000 kilohertz? The reason for that is at the IF amplifier stage, we feed this frequency 455 kilohertz to the IF amplifier stage, which does a very important job of both selectivity and sensitivity for the receiver. So both these things are being done at the IF amplifier stage in super heterodyne receiver. Now please understand, I'll talk about these two parameters. The receiver happens at IF amplifier, and if we talk about selectivity, selectivity depends upon Q factor. And if we design a receiver that works for all the frequencies, or in other words, if we subject this amplifier to a range of frequencies. Now for a typical amplitude modulated receiver, the Q factor will depend upon frequency, central frequency upon bandwidth, and uh, the range lies between 550 kilohertz to 1650 kilohertz for the central frequency, and the bandwidth is 10 kilohertz. So if we were to design the Q factor, or we were to find the range of Q factors that this amplifier would have needed to cater all the frequencies, central frequencies between the ranges 550 kilohertz to 1650 kilohertz, then Q factors range would have become 55 to 165. Reason being, the Q factor for 550 will become 550 upon 10, and Q factor for 1650 will become 1650 upon 10. 10 is the bandwidth for the audio signal. So catering to a range of Q factor from 55 to 165 would result in design complexities of the receiver. So that is why if we keep the central frequency at a fixed value of 450 kilohertz, which is here in this case, by selecting the value of local oscillator in such a way that it generates an intermediate frequency of a fixed value. So once we keep this as a fixed value, the Q factor will not change, and the Q factor will remain optimum at 45.5 value. And the performance of selectivity for a Q factor 45, or as a matter of fact for a Q factor in the range of 50 to 60, is at its peak. The selectivity happens best if we keep the Q factor between the range of 50 to 60, and we have chosen a value of 45.5. so that reduces the need of using very high power amplifiers, and it results in the reduction of harmonics also. So the first thing, parameter analysis, which is selectivity, happens better if we keep the frequency fed to the IF amplifier to be fixed. And the second factor, which is sensitivity, depends upon gain. So these two parameters, that selectivity depends upon Q factor and sensitivity depends upon gain, they must be remembered at all times for this IF amplifier stage, because if the gain increases, the instability of the system increases. Instability also increases, and we can expect higher gains for an IF amplifier stage if the frequencies become higher, and at a range of frequencies above 1000 kilohertz, the gain will result in the instability of the IF amplifier stage. And that is why, again, we would want this frequency which is being fed to the IF amplifier to remain constant and at a value which should give us a moderate gain. And the scientist Armstrong, he fiddled around with a lot of values of frequencies, and he found that 450 to 500 kilohertz range is the one that gives us an optimum value of gain, a moderate value of gain, and hence the system becomes stable. And once selectivity and sensitivity is done correctly by the IF amplifier, then of course this Fi is fed to the second stage mixer, and this local oscillator will also produce a frequency which is equivalent to Fi, because this is a synchronous mixer, and it will superimpose these two frequencies to give Fi here at the detector stage, and which is detected using a technique which could be any modulation detection technique like envelope detector or peak detector or whatever. So baseband signal is retrieved here. So if you're not clear about synchronous mixing for retrieving the baseband signal, I highly recommend that you watch the other video where detection process is explained separately. But at the output of the second stage, or a series of n stage detections which are synchronous, we get the baseband signal, which is further amplified in terms of audio and power to be made suitable for the speaker. And this is a push pull class B amplifier as mentioned in the previous videos. So this is how a superheterodyne receiver is different from the TRF receiver. A TRF receiver is a tuned radio frequency receiver that works for all the frequencies ranging from 550 to 1650 kilohertz, thereby making the selectivity and sensitivity difficult at the receiver. However, if we trim ourselves down to just one frequency of operation, these two parameter analysis become very accurate and easy. And this is what the theory or the thought process behind designing a superheterodyne receiver was. And I hope this discussion on superheterodyne receiver was of help. And if you liked the video, give it a thumbs up, consider subscribing to the channel. I'll see you in the next video. Take care. Bye bye.